Okay, let's dive into this explainer and unravel one of the absolute coolest magic tricks in all of physics. If you've ever seen a piece of metal just hovering there, locked in midair, spinning silently like gravity literally forgot to do its job, well then you've witnessed quantum levitation. Today, we're zooming in specifically on exactly why magnets levitate above superconductors, breaking down the mind-bending physics that makes this floating possible.
You know the clips I'm talking about. We've all seen those videos online, right? A small, frosty little disk floating effortlessly over a magnetic track, totally defying the laws of classical mechanics. It honestly looks like pure science fiction. But here's the thing. It isn't magic. It's actually a profound display of quantum mechanics operating on a massive, macroscopic scale. In this explainer, we're going to decode the exact mechanics from the tiny microscopic behavior of electrons all the way up to the macroscopic expulsion of magnetic fields to find out how, and more importantly, why that levitation actually happens.
To kick things off, check out this quote from physics professor Peter Lindenfield. It sets up this incredible dramatic tension. Magnetism and superconductivity are natural enemies. Think about that for a second. Macroscopic magnetism relies on aligning electron spins perfectly parallel to one another. But superconductivity? That depends on pairing electrons with their spins pointing in perfectly opposite, anti-parallel directions. So to get a magnet to just float above a superconductor, we are literally forcing two fundamental, natural enemies to work together in this state of perfect, delicate tension.
To ground this in reality, let's look at what you actually need to pull this trick off. Spoiler alert, it doesn't require a billion-dollar laboratory. All you need is a specific type of ceramic disc, usually something called yttrium barium copper oxide, or YBCO for short. Now, because this material only becomes superconducting at ridiculously low temperatures, you've got to bathe it in liquid nitrogen to cool it below its critical temperature. Once it's all frosty and supercooled, you just place a small permanent magnet right on top of it, and boom, levitation.
So let's look at layer 1, the phenomena.
When Walter Meissner and Robert Oxenfeld discovered this phenomenon way back in 1933, it completely shocked the scientific community. Just look at how the superconductor acts here. It's like a massive boulder sitting in a flowing river of magnetic field lines. It actively kicks the magnetic field out of its interior, making sure the magnetic induction, which we represent as B, drops to absolute zero inside the material. The magnetic field lines just have no choice. They are forced to bend and go completely around it.
So the absolutely crucial point here is the sharp contrast between a hypothetical perfect conductor and a true superconductor. If you had an ordinary metal with zero electrical resistance and you applied a magnetic field to it, Lenz's law tells us it would just generate currents to oppose any change. Essentially, it would just freeze and trap whatever magnetic field was already inside it. But a superconductor, it doesn't just trap the field, it actively evicts it. Even if the field was already hanging out there before the material was cooled, the exact second it turns superconducting, it pushes that magnetic field away, becoming a perfect diamagnet.
Moving deeper, let's check out layer 2. The microscopic mechanics. Okay, so what exactly is happening down at the microscopic level to push that immense magnetic force away? Now, don't let these equations intimidate you. Formulated by the brothers Fritz and Heinz London in 1935, they're actually pretty elegant. That first equation just shows that in a superconductor, electrons accelerate without any resistance. But that second London equation down at the bottom, that is the real star of the show. It proves mathematically that a magnetic field doesn't just hit a superconductor and bounce off like a tennis ball hitting a brick wall. Instead, it enters the surface just a tiny bit and then decays exponentially.
What you really should take away from this is the concept of the London penetration depth. It turns out the magnetic field actually just scratches the very outer surface of the superconductor, penetrating an unimaginably thin layer of maybe 20 to 40 nanometers. I mean, that is incredibly thin. Within this minuscule depth, the external magnetic field induces these persistent, perpetual screening currents running right along the surface. And these relentless surface currents act like an electromagnetic shield, generating an exact, opposing magnetic field that completely cancels out the external magnet's field inside the bulk of the material.
And you might be wondering, what on earth is powering these perfect frictionless surface currents? Well, enter Cooper pairs. In a normal metal, electrons are always bumping into things, lattice vibrations, impurities, you name it, and that creates electrical resistance. But in the superconducting state, electrons actually team up into Cooper pairs. These duos have opposite spins and momenta combining to form this coherent quantum state separated by an energy gap. And because thermal energy at these super cold temperatures is way too weak to break that gap, these paired electrons just glide through the material's atomic lattice without ever scattering or losing a single drop of energy. It's perfectly frictionless.
All right, on to layer 3, the secret to stability. Now here is the ultimate plot twist. If a superconductor perfectly repelled a magnet through that Meissner effect we just talked about, the levitation would be incredibly unstable. Think about trying to perfectly balance two magnets with their north poles facing each other. It doesn't work, right? The floating magnet would just slide right off the edge of the repulsive field like a wet bar of soap hitting the floor. So the real secret to stable, fixed levitation lies in the difference between Type 1 and Type 2 superconductors. Type 1 materials, like pure lead or mercury, show complete field expulsion. They just completely hate magnetic fields. But Type 2 materials, which include the complex alloys and high-temperature superconductors we actually use for levitation, well, they have a trick up their sleeve. At high enough magnetic fields, they enter what's called a mixed state. Instead of completely kicking the field out, they allow tiny, controlled amounts of magnetic flux to safely pass straight through them.
And this beautifully chaotic image reveals exactly what that mixed state looks like under a microscope. It looks like an intricate maze, doesn't it? Those dark normal regions are tiny microscopic tubes where the magnetic field is actually allowed to pierce right through the material. Surrounding those tubes are the lighter, superconducting regions where the Meissner effect is still in full force. We call these penetrating magnetic field lines quantized magnetic vortices.
So, following these steps, we arrive at this mind-blowing phenomenon known as flux pinning, or quantum locking. When those magnetic field lines from the floating magnet penetrate the Type 2 superconductor, they naturally seek out tiny imperfections and grain boundaries inside the material. The magnetic flux gets literally pinned, effectively locking those magnetic field lines in place. This creates a deeply, deeply stable anchor. It pins the magnet in midair so perfectly that it doesn't just float, it is locked in three-dimensional space. You can push it, you can spin it, you can even turn the entire superconductor completely upside down, and that magnet, it will remain perfectly suspended beneath it. No way, right? It's amazing.
Which brings us to the payoff, real-world magnetic levitation. Okay, let's step back for a second and look at the big picture. Why does this incredible quantum dance actually matter to our everyday lives? I mean, sure, it's really fun to watch a magnet float around in a lab, but how does this tension between magnetism and superconductivity actually serve humanity? Well, thanks to the Meissner effect and flux pinning, we are able to build absolutely world-changing technologies. We have frictionless, high-speed maglev trains that literally hover above their tracks, eliminating mechanical wear and massively reducing energy consumption. This exact same principle allows us to create the extraordinarily powerful, stable magnetic fields required for life-saving MRI machines in hospitals and even massive particle accelerators that are unlocking the secrets of the universe. On top of all that, this perfect quantum environment is absolutely essential for squids, which are these hypersensitive magnetic field detectors, and for building the superconducting qubits that are actively powering the revolution of quantum computing right now.
Which brings us right to the edge of the frontier. The biggest hurdle right now is temperature, right? We need liquid nitrogen or liquid helium just to make this work. But with scientists recently discovering hints of superconductivity at 260 Kelvin in highly pressurized hydrides, which is creeping incredibly, tantalizingly close to room temperature, we have to ask, how will a future of room temperature, ambient pressure magnetic levitation completely redefine our world? Imagine a society where frictionless transport, lossless energy grids, and quantum levitation aren't just locked away in freezing laboratories, but are just a normal part of our everyday lives. That is the magic we are inching toward.